All right, so my video capture software deal, it crashed. So I got to restart. But we ended up finding this function find peaks. It's pretty cool. Gave us an automatic little local maxima finder for our data. And we found out these peaks correspond to different data values in Y, and then data positions in X. So in this case, it's 135, right? 627, right? These kind of things. If we look at AMAG, the actual array of acceleration magnitudes, and we came in and looked at this. This is let's look at 269. So number 269, that's data point 16.6098. Let's look at all these numbers over here. Yep, that's indeed a local maxima, right? This is the highest number around, right? So we can see that when we plot this find peaks with just our data, we're getting back the location in the data structure that corresponds to that local maxima. All right, that's super cool. So let's run that thing. Let's go to our little help page, and we can plug in this find peaks locations deal, run that. And then if we look at locks, oh look, 269 is right there. We just now looked and made sure that's definitely a maxima. We let's look at AMAG of 390. Where's that? Keep going down. 390 is 16.18, local maxima. Wow. Yeah, this is giving us those data points, or that's luck. Probably not luck. All right, so we got peaks and locations, and we want to parse our data out so that we get this repeating characteristic signal. Okay, so how we're going to do that, we're going to extract the data from peak to peak. Right. So we want this AMAG data, right? We want the acceleration magnitude from peak 1 to peak 2. Right? So we got to name these. Let's say peak 1. We know that was 40 when we looked this thing up, right? That was location. We got 40. We got 135. Peak 2, 135. All right, so let's see what happens if we extract all the values from peak 1 to peak 2 in AMAG. Let's call that value, let's say AM equals this. Let's run that and then look at AM. AM is a 96 by 1 double. And it's got all these data points, right? It's got data points of AMAG from 40. It's like we came in and went from 40 and we selected all this data all the way to 135, right? And we just copy paste into this new thing AM. Copied and paste all that stuff in there. We did that with this code here, AMAG from peak 1 to peak 2. All right. So in general, though, what we could do is we could write locks of 1 to lox of 2, right? Remember, that's the same thing. Look, copy that in here. That's 40. That's 135, all right? So what if we did something like, you know, we wanted the first, we wanted the second, we wanted the third. All right, we could just write I is equal to 1 and go I here and go I plus 1 here, right? That's also the same thing, right? If we go run all this, say I equals 1, we do lox of I. Look, we get 40 again. Lox of I plus 1, 135. This thing works. Okay. What if I equals 2? All right, it's going to find the second peak to the third peak, and it's going to extract all that data from that, right? So let's see, AMAG here. Okay, yeah, looks like it changed. Looks like it's probably right. One way to check real quick is just to do a plot. We can do plot AM. Let's check that out. That looks pretty cool. Let's do I equals 3 and let's see if we get another one. Yeah, looks legit. Looks like we can, in general, we can just keep going through these I's and then, you know, make a bunch of different plots that have the same signal, right? So if we did that, though, right, we would only be able to look at one signal at a time. And we want to do something called an overlay. We want to overlay all of the data onto a single plot, and that's going to give us a comparison of these signals, all right? So to do that, the first thing we want to do is make a new figure. So just by typing the word figure, you're going to pop up a whole new figure window, right? You're going to, if we just type that in here, look, a blank figure window, it's a blank canvas. You know, you can plot whatever you want in it, right? So what we're going to do is plot AM in that for each I, right? And after we plot this stuff, we want to hold those plots in place. And we do that with this function called hold, and we input on into hold. And that's just how you do it. This is how you do it in MATLAB, okay? You say hold on or hold off. And by default, hold is off. You got to turn it on. Okay. So we do this. We say I equals 1. Let's run that. We get this thing. We go I equals 2. Run that. We get a whole new figure, right? It's actually not what I wanted to do. Let's go back and let's say, let's not make that figure in here. Let's make that figure here. So we'll open a new figure just like this, and we'll just keep running these I's in that figure. So here's the first one, right? If we go to I equals 2, run that. Now we got 2 signals. Go I equals 3. Keep going, right? And I gotta do this. How many times I gotta do this? Tell me I gotta do that 46 times? That's too many times. I don't want to do that. So let's do this. Let's do this with a program. Go for in a for loop. I equals 1 to how many locations we got? We got 46 locations. All right, 46. Let's format this stuff a little bit. All right, so look, we got 46 locations, but we want to go from peak to peak. We want to extract that data from peak to peak. And we're looking at peak I to I plus 1. So if we just did 46, in the last for loop, I is equal to 46. This is how these things work. So this is going to be a location of 47, and that thing doesn't exist, right? So this is going to throw us an error right here, right? So instead, let's go -1 up here. And this thing is going to say there's an array I that goes from 1 to 45. And the first for loop, I is going to equal 1. It's going to come in and say locks of 1, 2 locks of 2. And then the second for loop is going to be 2 to 3 and 3 to 4, and blah, 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 right? Keep going until you hit 45. All right, let's see what happens when we run this thing. Man, that's beautiful. We got all our signals overlaid on top of each other. And this thing looks pretty. I mean, I was walking pretty consistently, I'd say, right? I can say that this is a characteristic signal of me walking with my phone in my hand, right? So, you know, we collected enough data over a year or something. I could say this is Alex's walking signal when he has his phone in his hand. Okay, cool. So we got to, let's say, clean that up a little bit, right? When we look at this one more time, you can see that there's some like stray information that don't really like, right? So where is that coming from? We got the original plot. You know, wherever I started every time I started walking, I had some extra signal over here, right? And I don't really want that data, right? So let's clean this whole thing up by only finding the peaks for AMAG in basically the rhythmic section, the middle section. Let's crop out the first little couple seconds and the last little couple seconds over here. So how we do that is we have to make a whole new variable. Let's call this AMAG2 or cropped. Say cropped. AMAG cropped is equal to AMAG from what? Let's check that out. Let's say we start cropping here, say 98, and we stop here, something around 5402. 98 to 5402. So we want to go crop 98 to 5402. Take all that data and let's put it in AMAG cropped. And let's start using this as our signal that we want to analyze. Okay. So let's plot this one. Let's run this whole thing. Oh man, we got another error here. Index must not exceed 44. You're telling me location is going to change every single time I do these data analysis? That's gonna be a nightmare. We gotta fix that. So we hard coded the number of locations. That was maybe a bad idea, right? So how can we make that programmatic and just kind of work every time? Just gonna give us a for loop that gives us all these signals that we actually want. Well, let's look at locks gets has a size. This variable called size is a 44 by 1. I wonder if I could just put in this like size of locks. Heh, look at that. It's a function. Size gives us some amount of quantities in the quantity rows is 44. How many columns? It's 1. Wonder what happens if we say, remember from homework 1, where if we type in 1, that's the number of rows, right? That's the row direction instead of in the column direction versus the row direction, right? So 1 is the column direction and 2 is the row direction. If we type in 1, we get 44. That's the number we wanted, right? So we can just select this whole size deal. We'll put it into here. And then when we run, we don't get errors. That's beautiful. All right, so we got this nice repeating signal without much noisy signal. This is beautiful. This is exactly what we want. Is it? You know, we want some more information on this, right? This x-axis is not really complete. This is the number of data points. And we could do better than that. We could put an actual amount of time. So right now this is a unitless, you know, unitless amount of whatever data or whatever. All right, let's put some units on this thing, right? We can throw time on the x-axis just by coming in and using our timestamp, right? T, right? So let's do all of our analysis again with T in it. And you know what? I'm gonna say that go T of 1. I bet that doesn't look good, too pretty. That's like a whole date. It's like the date I did it and the hour and all this stuff. That's not gonna look too good. So let's look at this again. What if we did T1 is the initial time, so T0 is equal to T of 1. And let's say our general time that we want is equal to T. Let's say, yeah, equal to T, right? This whole vector minus T0. I wonder what happens then. T is now, oh wow, MATLAB has all this stuff. MATLAB says it's now a duration. T is now a duration, and it's got, well, it says it's 0, but you know what? MATLAB just shows you zeros, but it has all this millisecond data. And to prove that, I'm going to show you this. T of 1. And all right, you just got to trust me. But if you look up duration up here, let's go help duration. Let's see, we got seconds, minutes, hours, days, years, right? So let's look up seconds. Seconds converts durations to equivalent numeric values in seconds. So we got to type in seconds. Seconds of T. Let's convert this into seconds. All right, let's do that. Look at that. Now we got milliseconds on this thing, right? And our data is now double. It's no longer a duration or whatever, or some kind of weird freaking data type. It's now a double, and we got our time in milliseconds. All right, so we figured this whole thing out in the command window just by messing around. So let's convert that into our script. You know, I forgot what I did. So let's go to command window. We'll type in the up arrows, and we're just gonna kind of review what I looked at. T of 1, cleared that. All right, so I got T0 is have to equal T1, right? And then keep going up. Let's see. Oh, I made a variable called T, right? And that was this whole vector minus the initial time with all the date and stuff. And remember that spit out this whole duration type signal. So then we had to clean that up somehow. What do we do? Oh yeah, we converted to seconds, right? So we can, there we go. Now t is in seconds. All right, so all of that was just kind of to show this kind of crazy MATLAB thing, how to convert your duration, your timetable duration thing into milliseconds. Okay, cool. So now we can do all of our analysis. It's kind of the same thing. We can do all the stuff we're extracting from t. We can do that again over here. You know, we can, all the locations for t correspond to the same AMAG, everything. All right. So let's go ahead and in here, actually, so this right here, if we were going to plot the entire signal, we would probably put t and AMAG cropped, right? Let's look at this. Actually, we got to do t cropped because we modified the AMAG crop, right? So we got to do the same thing to t. T cropped equals t from that to that. All right, cool. So let's go t cropped. Gotta make it first. There you go. The whole thing. Okay, so look. Now the bottom is no longer like thousands of data or something. Now it's in seconds. So that's nice. Definitely what we want. But what happens if we put t down here and we did this whole thing like tm is equal to t cropped from peak 1 to peak 2. And then we plotted all of these things with tm and am. I don't know if this is going to work. Yeah, it doesn't work, right? It doesn't work because essentially all we did was we cropped that signal and then we put it all back together. All right. So what we want to do instead is make a characteristic array of data points, right, from AM. So we're going to get rid of this whole thing right here. All right. But we do want time on this plot we're making, right? We want to know how much time this is, right? Because these data points have to be scaled in the X direction and stuff like that. It'd be nice to know how much time that is. So let's come back and say we gotta subtract our T0 again. We got T cropped 0, right? And that's going to be equal to the starting time. So the starting time from that peak. Right? Well, how do we do that? Oh yeah, first peak has to be up here. That's the location of it. Right, so T cropped 0 is gotta be T cropped of peak 1, right? The first peak, wherever that time was on the first peak, right? We're gonna put in the T crop 0. And then now we can extract that whole TM thing that we did before. T cropped from peak 1 to peak 2, just like we did in AM. Right, we can do this whole thing again, just like this. and then we can subtract the time to cop 0. Take that away, right? Subtract that initial time from our new array. When we do that and we plot TM in here, we'll see what happens. Oh, we got what we want now. We got 0 to like 1.2 or something. So it takes about 1.2 seconds per step for me to, whatever, walk or something, So I'm looking at about a hertz, 1 hertz, 1 step per second. Okay. Cool. So, what else we got to do with that plot real quick? First of all, this plot doesn't have any title or axis or anything like that. So, let's go ahead and throw all those things on, right? So all we got to do on our little plot here, let's say we did all of our plots, we got to type in a title. And we're going to name this. This one's going to be AJM walking in the hand. So I'm going to call it hand, walking hand. Do that one. Now we got this title up top, right? That's going to identify this whole plot so that we can differentiate all the plots we make. It's going to be great. It's going to be great. Yeah. Let's go. Let's do this one thing real quick. I want to show you. If we go to tools, or what is it here? No. Yeah. View, property editor. That's going to come in and we can completely modify all of the plot, right? We can do anything we want. We can click on this side. We can put an x-axis label. We can go say this is acceleration magnitude. Oop, that is x. This is time in seconds. And this one's acceleration magnitude. And that's meters per second squared. Okay. So we can also change the font size of these things. We can go and say, where's the font? There it is. Font size, I could do with a little bigger font size. That'd be great. Okay. So you can do tons of things with this, right? You can say your y-axis should have limits from 0 to 18. It's really nice usually to have all of your plots start from zeros. That way everyone gets some bearings. And your acceleration should always go to some like maximum value for all your plots. So all your plots should have the same-ish y-axis, right? So if you look at jogging, look at walking upstairs, we want to always plot with the same y-axis. Cool? All right, so this looks like a good plot. I like this thing. I want to export it. So what I do is go up to File. I can, if I save from right here, I'll just I'm going to do is save the MATLAB figure. I don't want to do that unless I want to be able to modify that figure again in the MATLAB window. If I want to save it as a say JPEG or PDF, PNG, SVG, TIFF, whatever, right? I just select the type I want and then name it. And so this is HAM hand, right? I want to save that, right? now it's over here, and I can open that outside MATLAB in my photos. Cool. That's a figure I can put into Word, no problem, right? So go ahead and do all the analysis for all these different conditions. Remember that you're going to want to have repeating data, right? So anything in the hand, you could have some tricky situations where it looks repeating, but it's not. That's like, think about if your arm is swinging back and forth, or you have some weird signal like that. You can see that one full cycle per step is going to have like 2 different types of peaks. So keep that kind of stuff in mind. Keep the kind of the background, the what you were doing when you made that data in mind for your analysis, right? Okay, so I think in the next video we're going to look at some fancy type of plotting, like envelopes and some signal analysis. Just taking all this analysis and doing some standard deviations and cleaning up the data and making a standard signal analysis that we can say, here's the average for this person, this person, this person, this person, and then we're going to plot all that together, right? Cool. See you in the next one.